Okay, the last talk in this session is invited talk, and we have Dr. Arne Heimendahl from the University of Köln. Okay, and can you share the slide?
Sharing the screen.
Okay, please start.
All right. Yeah, thanks for the invitation and thanks for organizing this workshop. And sorry for this small delay. Today I will talk about our paper, the axiomatic and the operational approaches to resource theories of magic do not coincide. And it's joint work with Markus Heinrich and David Groß. Markus Heinrich was a PhD student at Cologne and is now in Düsseldorf, and David Groß, who's my supervisor. And I'm not a doctor, I'm also just a PhD student. And you can find the preprint on the archive. Well, I have to say that we are currently working on a second version of the paper, and so there we have simplified proofs and some stronger statements. So if you really want to give it a read, maybe it's worth waiting a little bit until we publish the second version. All right, so what will I talk about today? First of all, I will talk about stabilizer operations, Gottesman-Knill and magic state distillation. Then I will talk about completely stabilizing preserving channels and really stabilizer operations that we've already seen during the last talk, and completely stabilizer preserving channels that will be the two protagonists of this talk and their relation to each other. Then I will introduce our main result, and in the end I will just talk a little bit about the techniques that we use. All right, so first of all, let me start with a little bit of motivation. So the model we are dealing with is the magic state model of quantum computation, and this is a fault-tolerant model of quantum computation. It's really, one of the leading models for near-term quantum devices, because you can implement stabilizer codes, and these are kind of the leading models for quantum error correcting codes. And in this model, your resource is usually called magic, that we've already seen during the last talk. And this magic is usually, in the one qubit picture, one state on the Bloch figure outside this small octahedron here. And what you have to do in this model is you have to use and you have to prepare this magic. So sometimes you have to transform it. And well, to operate on this resource, you can use two types, or depending on your task, you can use two types of free operations. So one of them are stabilizer operations that we've already seen during the last talk. They are defined in an operational way. And the other operation that you can use are completely stabilizer preserving maps or channels, and they are defined axiomatically. And now the question is is one of these two classes more powerful than the others, or how are they related to each other? And as the title alludes, we will see that these classes are indeed different. One important feature that we always have in this resource theoretic framework is that, well, these two kinds of free operations, they will not generate any resource, so they will not increase the amount of magic that we have in our system. Okay, by the way, if you have any questions, just interrupt me. Maybe it's better to ask during the talk than to wait until the end. Okay, so now let's start with stabilizer operations. What are stabilizer operations? These are certain quantum circuits that consist of one of these four operations. So the first thing we're allowed to do are preparation and measurements of computational basis states. So, well, if you look at this first point, we can take as an input some computational basis state, and we can just perform a measurement on this computational basis measurement. Then we're allowed to use applications of phase gate, Hadamard gates, or CNOT gates, or we can use several of them. And if we consider the group that they generate, the multiplicative group, then this is the Clifford group. So essentially, we're allowed to implement any Clifford gate. Then we're allowed to use classical randomness. So this means we can do, for example, as you can see on this third point, we are allowed to do a measurement with probability p, or we're allowed to do a unitary with probability 1 minus p. This feature makes this set of stabilizer operations convex. So convex combinations of stabilizer operations, this is something that you can achieve using classical randomness. So this is again a stabilizer operation. And the fourth thing that we can do is we can condition all these operations on previous measurement outcomes. So in this fourth small example, what you can do is we measure some computational basis state, and then conditioned on the outcome 0, we apply a Hadamard gate, or conditioned on the outcome 1, we apply a phase gate. So things like this are also possible. Well, this is a very nice model. It's very well studied, but there's one major drawback, and this drawback is the Gottesman-Knill theorem. And this says, if I just restrict myself to this model, then I can efficiently simulate this model classically with my normal computer. So this has not the full power that we expect from a quantum computer. But however, this model has a lot of nice features. We can implement quantum error correcting codes like stabilizer codes. So kind of we want to use all the nice features of this model, but we need some extra ingredient or some extra resource. And this extra resource are magic states. So we can use certain states to implement other gates that are not Clifford gates. So for example, we can use the T state to implement the diagonal T gate with a 1 and e to the power of I pi over 4 on the diagonal. And we can implement this just using a stabilizer operation. So when our circuit has as an input a T state and another state psi, then we can use a stabilizer operation consisting of a C0 gate, a measurement, and a phase gate together with a Pauli X rotation to implement this T gate on our state psi. Or as we've seen in the talk before by Bartosz, we can also use the T state to implement a CCZ state, which is also a non-Clifford gate. And now a fact is that stabilizer operations plus magic states, this gives us a universal model for quantum computation. So this model has the full power of a quantum computer. One other thing that we can do that we've already seen in the talk before. So for example, if we're in a lab, usually we don't have access to an ideal magic state, but we have maybe access to n copies of a corrupted state, then we can use stabilizer operations to purify the state in the direction of T. So we can distill this magic state. And then, with another stabilizer operation, as we've seen before, we can inject this state into our circuits and implement a non-Clifford T gate, for example. So what we see here, to make this whole model universal, magic is the necessary resource. Okay, so let's just briefly explain resource theories in a nutshell. Well, probably all of you are very familiar with this. Probably you're also more familiar with this than I am. So usually in this resource theory, you have something that you call free operations. And these free operations, they preserve a certain set of free states. And then your extra resource, so your magic states, are obviously not included in this set of free states. So they are somewhere here in this state space, but not in F. And these free operations, they have one feature: they cannot generate any resource. So they can preserve the set of free states, but they will not generate any resource. And now you can define these free operations in two ways. So you can do this operational, as we've seen before with stabilizer operations. So in the sense, prepare this, apply that, measure those. So you have concrete, explicit operations that you could use to achieve this. The other way to define these free operations is axiomatically. And axiomatically here means, okay, free operations are just all operations that preserve my set of free states. Let's consider a very famous example, and this is the resource theory of entanglement that we've already seen in the talk before. So here, our set of free states are product states, and the free operations are operations that preserve product states. So on the one hand, you can define them operational, so you allow local operations and classical communication. So if you look at the small picture, Alice and Bob, they can do local operations on their subsystem. They can classically communicate with each other. But if you just allow these operations, then separable product states are just mapped to product states. And the other kind of way how you can define a free operation is you can do this axiomatically. You just say, okay, I consider all channels that preserve product states. And now, again, if you have any sensible measure of entanglement, this should be non-increasing under the two classes SEP and LOCC, because this is the feature that you expect from free operations. And now, a famous theory in entanglement theory is the following. So if I allow k rounds of local operations and classical communication, then this is a strict subset of LOCC with k+1 rounds, and so on. This is a strict subset of the set of all LOCC operations. This is a strict subset of its closure, and this is a strict subset of the class of all separable channels. Our goal is to find a distinction like this just for stabilizer operations and completely stabilizer preserving maps. So, okay, let me just like introduce the resource theory of magic. So in this model, our free states are not separable states, but these states, our free states, are those that can be prepared by stabilizer operations. In the case of qubits, later we'll talk about what happens in the case of qubits. So I said our free states is the stabilizer polytope, and this is simply the orbit of the zero state under the Clifford group. This is exactly all that you can prepare with stabilizer operations. And it's the convex solve because, as we've seen before, stabilizer operations, they also include the use of classical randomness. In the one qubit picture, what you obtain is this nice octahedron with its 6 vertices within the Bloch sphere. And these red vertices here are precisely the stabilizer states. And what are your free operations? We've already seen them. On the one hand, you can define them operationally, and on the other hand, you can define them axiomatically. And axiomatically here means simply stabilizer operations, completely stabilizer preserving channels are exactly those that preserve this polytope SP. Now the question is, are they the same? And kind of a small teaser, as the title alludes, they will not be the same. Okay, so let us define completely stabilizer preserving channels more rigorously. So what are they? A linear map is completely stabilizer preserving if it preserves the stabilizer polytope. And not only if it preserves the stabilizer polytope, but also if I tensor it with some identity map. So if I have the n plus k qubit stabilizer polytope, I consider the map E tensored with the identity on k subsystems, then this should also be a subset of the n plus k stabilizer polytope. And note, well, this is very similar to the definition of completely positive maps. So here you would just replace the stabilizer polytope by the cone of positive semi-definite matrices. So, and there you know, well, positive is not the same as completely positive, and this is exactly the same case as here. So stabilizer preserving is not the same as completely stabilizer preserving. And what else do we have? Well, stabilizer operations, they are all completely stabilizer preserving channels. So if I take a stabilizer operation, I tensor it with an identity on k subsystems, I will just obtain and I consider the image of the stabilizer polytope. Then what I obtain will also be within the stabilizer polytope. And well, maybe one thing to note here, you could also define CSP maps from n qubits to m qubits, but for simplicity here, we'll consider only stabilizer operations and CSP maps that map n qubits to n qubits. Then let us prove a small and easy lemma. So each of these CSP maps is a quantum channel, so it's a CPTP map. So how can you do this? First of all, it's completely positive, but this is pretty easy to see because the maximally entangled state is a stabilizer state. So we can use the Choi-Yamlokovsky isomorphism. And if we plug in the stabilizer state in my CSP map E tensored with the identity on n subsystems, then, well, this is by definition, because E is a CSP map, this is once again a stabilizer state, or state within the stabilizer polytope. And the stabilizer polytope, well, it's the convex solve of pure states, so it's a subset of the cone of PSD matrices. So the choice state of every CSP map is a stabilizer state, and so it's also just a state. So it remains to prove that every CSP map or every CSP channel is trace preserving. Well, this is also very easy to see because, well, if you consider a stabilizer state and its image under this map E, then you obtain a stabilizer state again. And well, these are states, they have both trace 1. So know that a CSP map preserves the state, the trace for all stabilizer states. And this means in turn, stabilizer states, they generate the whole state space or the space of Hermitian matrices. So I can just extend this statement linearly, and I obtain that every CSP map is also trace preserving. So this, well, tells us that this definition makes sense. So all CSP channels are really quantum channels. And we can even go a little bit further. So if I take a CSP channel, then it is CSP if and only if its choice state is a stabilizer state. So if you compare this to choice theorem, if well, a map is CPTP, if and only if its choice state is positive semi-definite and it preserves the trace. And this is pretty nice because this allows us to do the following. This allows us to encode all CSP channels in a polytope, and this polytope is simply the 2n-qubit stabilizer polytope intersected with this trace-preserving condition. And this trace-preserving condition here is simply can be represented by an affine space. So all completely stabilizer-preserving channels form a polytope, and this is simply the 2n-qubit stabilizer polytope intersected with the affine subspace that it is induced by this trace-preserving condition. And now you might ask, okay, well, we have a polytope. If we want to describe a polytope, what you're usually interested in, you're usually interested in the vertices of the polytopes or the extreme points. So you're interested in these, well, in this small picture, you would be interested in these 4 points here. And kind of, we will give a partial answer. We'll also characterize some of its vertices here. Well, we've seen, okay, we can describe CSP channels via their choice state. We can also find an explicit Krauss decomposition of these CSP channels. And this looks the following way. So essentially, we have a convex combination and these over Krauss operators. And these Krauss operators are the following. So I conjugate my input by some Ci times Pi. And the Ci's are Clifford unitaries, and the Pi's are stabilizer code projectors up to some normalization factor that I just swept under the carpet here. So what are stabilizer code projectors? These are projectors onto certain orthonormal bases of stabilizer states. And well, this is the Krauss decomposition, and then you can simply translate the TP condition into something that relates to the affine map. It's also completely standard. So if to the adjoint map, so if the adjoint map maps the identity to the identity, then I can just like plug it in here on the right and then obtain that the only thing that remains are these PIs and the lambda i's. So I have a CSP channel if it has this form and it satisfies the trace preserving condition. And now this gives us a nice way to interpret these CSP channels. So essentially what we do is we perform POVM, because this condition that we have here is a POVM condition. So we perform a POVM with operators lambda I pi, and once we measure I, then we apply a condition Clifford unitary Ci. All right, so let's consider some examples. Well, the easiest example is simply mixing Clifford unitaries. So what do? I just conjugate my input with a Clifford unitary and do this with probability lambda I. Another example is I do computational basis measurement, and conditioned on outcome X, I apply Clifford unitary Cx. In this small picture here, I just do, for example, a measurement in the basis 0, 1, and if I measure 0, I apply unitary, well, this is a typo, unitary C1, or conditional on outcome 1, I apply unitary C2. And what can we do? Well, we could also replace the computational basis here by any other stabilizer basis, and we would still obtain a CSP channel. Well, one observation is, well, it was very easy to really like explicitly describe what these channels do. So these channels are stabilizer operations, because kind of we can really like define what we're doing here operationally. And kind of our goal is to find a CSP channel that is not a stabilizer operation. So we have to find something that is a little bit more elaborate here. And this is also the main result of our paper, which says that stabilizer operations are a strict subset of the set of CSP channels for more than 1 qubit, and for 1 qubit, they are the same. And how do we do this? Well, kind of, we only have to do one thing. We just have to find one CSP channel that is not a stabilizer operation. And along the way, in order to get a certificate that our constructed channel is not a stabilizer operation, we characterize certain properties of extremal stabilizer operations and CSP channels. Let me briefly comment on the case n equals 1. So here, extremal CSP channels and stabilizer operations are pretty simple. So all what we can do is we do a measurement in some orthogonal stabilizer basis, and then if we measure outcome 0, we apply unitary U1, and U1 is again, C1 is a Clifford unitary, and condition on outcome 1, I apply a Clifford unitary C2. And these orthogonal stabilizer bases, well, if you look at the stabilizer polytope for 1 qubit, then these are exactly these opposite vertices here. So, well, in this block-shaped picture, they do not seem to be orthogonal, but kind of if you just write them down completely, then orthogonal stabilizer states are exactly states that are opposite here in this picture. So if the one state is on top here and the zero state, for example, is on the bottom. Okay, so far so good. Yeah, let me briefly comment on the difference between qubits and qudits in this framework. So essentially, all objects that we have considered, they also have a qudit analog for D being some odd prime. So stabilizer states exist for qudit systems, stabilizer operations. Magic state distillation can also be performed for qudit systems. CSP maps have their analog. And kind of our counterexample, that is a CSP channel, but not a stabilizer operation, that also has a qudit analog. And we're also writing like one part of the paper with this generalized channel. But however, you should rethink the resource theory in this setting, because in the setup of qudit systems, for D being some odd prime, your set of free states should be states with a positive Wigner function, or states that lie in this Wigner simplex here. Because yeah, if you look at the literature in this area, so you can find very nice classical, efficient classical simulation schemes that are only related to Wigner negativity. So here we get a bigger set of free states. So this is not just the stabilizer polytope, but we just extended by this bluish parts, by just 3 bluish parts here close to the vertices of this triangle here. So we obtain a bigger set of free states. And well, if we consider a bigger set of free states, then we should also consider a different class of free operations. And these free operations should be exactly those that do not increase Wigner negativity. Or you could also say free operations are exactly those that preserve the Wigner simplex. So they are, which are in some sense completely Wigner simplex preserving. And like people also develop a resource theory for this case. All right, so now let's get to some more technical details. So how do we prove that SO is a strict subset of CSP? So as I said, what we want to do is we want to characterize properties of extremal stabilizer operations and CSP channels. And what we do is, well, we simply characterize certain properties of extremal stabilizer operations, and when we just find an extremal CSP channel that does not have these properties. Because, well, if we had a CSP channel that is extremal in the set of CSP maps, then it's also extremal in the set of stabilizer operations, because SO is a subset of CSP. And well, this is our very good looking example. So this is the channel. So what does it do in the computational basis? So if I take an input state rho, then it maps well, rho 0, 0 to the plus state, or rho 0, 0 times the plus state, and then it preserves the remaining diagonal, and like it reduces all off diagonals by, or scales all off diagonals by 1/2, except for the first column and the first row. They are just sent to 0. And we also will kind of describe this channel operationally later. What is our claim? Well, this channel is completely stabilizer preserving. So it lies somewhere in this polytope here. Well, if I consider the choice state, then completely stabilizer preserving meant that the choice state is exactly in the polytope here. Then we claim that is an extreme point, so it's a vertex of this polytope. And what we also claim is that it's not a stabilizer operation. All right, so let us decompose this channel first. Okay, so what does this channel do operationally? Well, okay, it's not a stabilizer operation, so we just like use operations that are not necessarily stabilizer operations to realize this channel. So the first thing that it does is it performs a projective measurement of the following basis, of the 0, 0 basis and its complement, so the identity minus the 0 state. So, and what does this result? And this results in this step 1. So what we obtain is kind of the first entry of my density matrix, rho 0, 0 times the 0 state plus the remaining matrix, where I just set the first column and the first row to 0, and I just preserve the rest. And then what it does do in the second step Conditioned on 0, I just perform a Hadamard on all qubits, and this Hadamard maps the 0 state to the plus state. And well, if I measured 1, so if and in the second case, then I do a partial dephasing in the computational basis. So what I do is with probability 1.5, I just don't do anything, and with probability 1.5, I do a computational basis measurement. And well, now we have these 3 steps that we perform, and kind of the crucial thing here is that this first operation here is not a stabilizer operation, and this may allude to the fact that we're considering some channel here that is not a CSP channel. Yeah, and yet now you might ask, okay, well, we have this very strange channel that we came up with. How do you come up with such an example? And kind of our initial idea was the following. Okay, we just try to find a sufficiently complex extremal CSP channel. So we try to find a sufficiently complex vertex of of the CSP polytope. And therefore, kind of, we just like recalled what the Krauss decomposition of such a CSP channel was. So it was given by this, where the Krauss operators were products of Clifford unitaries and stabilizer code projectors, such that this trace-preserving condition is satisfied here. And then kind of one feature of stabilizer operations is the following. So usually, well, if this was a stabilizer operation, then these PIs would be orthogonal. So then I would have orthogonal PI. So PI times PJ would be 0. And now what we just tried to find was kind of was a set of stabilizer code projectors that satisfied this condition, but that were not orthogonal. So we try to find as many of them as possible that are non-orthogonal and that have huge overlap, such that this condition is satisfied. Well, why do we need this large overlap? This large overlap in some points in the direction that the channel that we have at hand is indeed a vertex. Okay, now how did we finally prove that this is an extreme point of the CSP polytope? So we just focused on certain extremal properties of this channel. So, for example, if you evaluate this channel at the 0 state, then kind of the second summand and the third summand, they will just vanish. So all that remains is simply plus plus. So the 0 state is mapped to plus plus. And if I evaluate the channel on another computational basis state, then, well, this first sum will vanish and the third summand, they will vanish. So it will only like survive one summand of the second sum here. So it simply preserves computational basis states. So our channel lambda is a subset of the set AD, and this set AD is what we call the set of almost diagonal channels, because they preserve the diagonal except for the first entry. And then, well, you can prove an easy fact. So if you have if you have some channel that preserves parts of the computational basis or maps parts of the computational basis to pure states again, then you can easily prove the following thing. Such a channel is simply a phase of the set of all quantum channels. And now, well, this AD, so the set of all almost diagonal channels, this is this phase here of the set of all quantum channels. Well, the set of all quantum channels, this is not a polytope, this has curvature at some points. It's a very high dimensional object with a very elaborate structure. But now we have this phase, and while we know that lambda is in this thing, we also know that lambda is a CSP map, what we haven't proved here, but which you can also prove using this Krauss decomposition. And then within this framework, it was not too hard to prove that lambda is the vertex of this phase AD intersected with CSP. And well, if it's a vertex of a phase of CSP, well, AD is also a phase of CSP because it lies on the boundary of the set of all quantum channels, and CSP, this set of CSP channels is also a subset of quantum channels. So yeah, we know that lambda is a vertex of this phase, and this also already tells us that lambda is also just a vertex of the polytope of CSP channels. Okay, so to prove that lambda is a vertex, just we considered certain properties of this channel, and then yeah, we try to find a reduced framework where it was possible to show that this is indeed a vertex. Okay, well, once you know that lambda is a vertex of the polytope of CSP channels, we are able to show that lambda is not a stabilizer operation. And here I will present like 2 ways to do this. And the first way is based on Pauli invariance of extremal stabilizer operations. This is also, so this is kind of a property of extremal stabilizer operations, and this is the following. So either my extremal stabilizer operation is essentially a unitary on larger system. So what I'm doing is I have my input, I tensor it with some 0 and chiller states, and then I act on this state with a larger Clifford unitary, and then I possibly trace out some qubits. So in the picture, as your input, you have rho and like R copies of the 0 state. Then you apply a large Clifford unitary, and then you trace out. So we call this a Clifford dilation. So either your extremal stabilizer operation looks like this, or it has a certain Pauli invariance. And this means that there's a Pauli matrix such that when I conjugate my input with this Pauli matrix, I simply obtain the same channel. So here in this picture, I could just apply E, or what I could also do is I could first apply, first conjugate my input with a Pauli matrix, and then apply E. Okay, and well, the second point has the following consequence. So if I have another Pauli matrix U that commutes with my Pauli matrix W here, that anti-commutes with this matrix, then the following happens. So then if I evaluate my channel E at this Pauli matrix U, well, then I know this channel E is invariant under conjugation with W. So I can just conjugate U with W. Then I can use that U and W, they anti-commute. So I get a minus, well, everything is linear, so I can just pull out the minus. Then these W's, they just cancel. So in the end, what I have is that E of U is minus E of U. And well, if I have something like this, this means that E of U has to be 0. So this Pauli matrix U that anti-commutes with W lies in the kernel of my channel E. And now to prove that my channel lambda is not a stabilizer operation, well, we know it's extremal. So if it was an extremal stabilizer operation, it needs to satisfy one of these 2 properties here. It would need to satisfy one of these properties here. So it suffices to show that lambda doesn't have Pauli matrix in its kernel, and that it is not a Clifford dilation. And these are 2 things that, well, if you have this explicit form of your lambda channel, these are 2 things that are not too hard to do. Okay. Another way to prove that lambda is not a stabilizer operation is more geometrically. So here we just recall that lambda was in this set of almost diagonal channels. And now what you can also do is you can characterize the intersection of stabilizer operations with almost diagonal channels. And then, well, once you have this, you obtain a phase of, well, this is again, well, the phase of the set of stabilizer operations. And then what you can do is you can simply separate this set with a hyperplane, because, well, the set SO intersected with AD is not too hard to characterize. So in the picture, somewhere here, you have the intersection of SO with AD. Lambda is somewhere here. And all you have to do is you have to find some separating hyperplane that separates this phase SO intersected with AD with the lambda channel. Okay, yeah, with this, I'm almost at the end. So what did we do in our work? So in our work, we studied the class of quantum channels, namely the channels CSP and SO. We proved that the class of CSP channels strictly contains all stabilizer operations for more than 1 qubit, and that they are the same for 1 qubit. And what we did is we really investigated in structural properties of stabilizer operations and CSP channels. And well, here's some open questions. So the first open question is the following: is this set of stabilizer operations a polytope or not? So well, we have this strong feeling that it is a polytope, and this is also kind of due to the following statement. So extremal stabilizer operations, they usually have the following form, or you can prove that they have the following form. So what you do is, to your input, you place a measurement operator pi, which is once again a stabilizer called projector. Then you tensor your input with some ancillar state, and then you act with a global Clifford unitary ui on this whole thing, and then you just trace out some qubits. And while to prove this theorem, this kind of was based on ideas of Campbell and Brown and Bevel that kind of derived a similar form for certain stabilizer operations. And now, well, if you want to prove that SO is a polytope, yeah, it would suffice to prove that you can also find a normal form, so that every channel that you have here can also be written as a channel where you do not use these ancillar qubits here. So where you have some form which is just like UI, PI row, PI, UI dagger, you just don't have to tensor with some ancillar system, and you don't have to trace out something. For example, in this case of almost diagonal channels, so if your stabilizer operation is an almost diagonal channel, there we were able to prove that you don't need this ancillar qubits. So there we were able to prove that you could find, well, a form that does not use these extra ancillars. Another thing that would suffice is just to restrict the amount of ancillars. So if you could say, okay, we don't, like, R cannot, so every extremal stabilizer operation has a representation like this, and R is, I don't know, smaller than or equal to N, then you would also be ready, because then, you know, there's just like a finite amount of shapes or forms that such an extremal stabilizer operation can attain. And this would tell you, okay, well, I just have a finite amount of extremal stabilizer operations, so I would just have a polytope. Well, one other open question we're interested in is, well, we found this separation by some very specific channel. Well, are there implications for magic state distillation? So we've already seen, well, we have 3 states in the talk before. You can find like bounds on distillation rates of magic states, or bounds on distillation, yeah, on protocols that give you give you like T gates out of magic states. So can we kind of achieve better rates using CSP channels than stabilizer operations? And yeah, one other question, well, we came up with this weird lambda channel. Well, can we use this for any like practical tasks? So it's really abstract things, but well, we may wonder, okay, can we also use this channel for something more practical? All right, so yeah, with this, I'd like to conclude, and I'd like to conclude with a small quote, which I really didn't stick to during the talk, but nevertheless, I find it's kind of a funny thing to say.
Okay, thank you very much for a wonderful talk. And are there any questions for the speaker? We have some time left, so you can ask some questions. Okay, I have one question. So do you have a concrete example of operational tasks such that the CSP operations strictly outperform the SO operations?
Well, this is exactly one of the open problems. So, well, exactly, this is one thing that we'd like to do, but we have no idea of this. So this is kind of really a thing for further research, because, well, if you consider the example of LOCC operations, and you compare like LOCC operations with separable operations, there you really have, like, in terms of entanglement distillation, there you can really prove that they that separable channels are better for certain tasks, and something like this does not exist yet. So it's kind of, our work was kind of a starting point for more research in this direction.
And also in the case of state discrimination in LOCC example.
Exactly, yeah.
Okay, are there any other questions?
Well, otherwise you can also ask them in the Slack channel. Yeah. So I'll look at that as well.
Okay. Okay. If you have no more questions, then let's thank the Dr. Arne. Let's thank the speaker again.
Thanks.
And also let's thank all the speakers in this session. And okay, this is the end of